So in this case, whenever we run this, what we would have done, especially for the, did I ask you for the dummy variable model or just the, which ones did I ask for? Let me make sure. Let's make sure I'm giving you the right information. So I asked for, yeah, fixed effects, first difference. Okay, so I didn't even ask about the dummy variable model. What you would do in this case is basically run these exact same models, but you would just add in two new factors within the model. So if I was to run this, I would basically add on to this. Let's see here, where are we at? Well, I'm not going to do the dummy variable model. Let me just get rid of that one. So one is we would want it to add in the dummy variable model for year. That's the first thing, right? Then I could go through and then try to combine the OCC again, or I could just ask it to add them. I can't remember the shorthand for this, so I'm just going to copy and paste these in. Yeah, like I said, this is not going to be the quickest method of doing this. Mm-hmm. Why is what? Oh, this would be the dummy variable model. So basically all we're doing is adding an individual dummy for each of the IDs, but it doesn't change the method. We're still going to use OLS. That's why usually you won't see it called DV, you see it called LSDV, which means least squares dummy variable model. And it's just, I didn't ask about that one in the practical, that's why I didn't change it. Let me just get these. Don't do that. Okay, and then let's see, so I told it to factor the year, I told it to, yeah, that should be fun. Gotta do all that. So then if I told it to do the summary, what did I call it? Model? Yeah. Oh, flipped around. So that would be the version for the fixed effects. Okay? But again, just like I said before, it's going to change or to remove education, black, and Hispanic, and it keeps in anything that's varying over time. Only thing we've done here is just added a dummy variable for each year, -1. So this case, I know that it threw out 1987. And I know there's 9 occupations, so I left off occupation 9, and so I did that myself. So that's why it's not going to show up. But again, you're going to notice just because I'm including these are meant to be controls in various forms. But I'm not really concerned too much about whether they're significant or not, because they're not my primary reason for doing this. But there is something that we can do, which could be kind of, well, Whether it works or not, we'll see if that's the case. Let me see something. Yeah. Yeah. Those are free. I could have tried to do it in a fancy way, but usually that ends up me messing something up. So I just threw them in there real quick. But I was going to try to change one thing if it doesn't mess anything up. I was going to try to show you there is a way of including variables that are time invariant in these types of models. Whether I do this properly or not, we'll see. Come on, where are you at? Yeah. You have to tell it it's a factor. If you put in year, it's going to think it's a continuous variable. You have to identify it as being, we're looking at if 88 versus everything else, if 87 versus everything else. If you don't, it's going to consider it a continuous variable. That's not a factor variable or a dummy variable. So we have to put factor in there, or you have to tell it something like you would have to do something like this. So wage pan year. Oops. You would have to define it within the data set. Where did that go? Those are occupational dummies. So I could define it as a factor, and then I wouldn't have to put factor in the equation if I did it that way. Just take that away. I just wanted to show you this if I did it right. Hopefully I did. Now, remember the education that got thrown out? Now, remember I was telling you there's ways of bringing things back in when they're time invariant, as long as I interact them with things that are varying over time. In this case, I just randomly chose one of them. I chose occupation. And by doing that, I can bring that information back in, which then it's just about the how do you talk about it, if that's your reason for bringing in, how do you interpret it? So that's why you just have to be careful in how you're interacting things. But it is a way of bringing back information that you care about and you don't want to lose. Okay? So I could do the same thing for the other models. So if I'd basically just rerun this before I made that little multiplication thing, or that interaction. I would just run this for the FD model again. But again, remember what I told you before. Because of the way I structured this to show you that things are falling out or staying in, you would really want to run this by removing this, this, and this, and then you can include your dummy variables for the years. But think about what the first differencing model is going to do with any type of year dummy variable. What does it mean in a difference for a year? So it's not as important because it is just a control, but just note that they're not going to fall out. It's going to be differences between each year because there's 1 and zeros. 1 year, the difference of the first year from the second year is going to be 1, and then the next one is going to be, there's going to be little changes as you go along, right? But they're still there as controls for the year, even though they are differenced out. Same for occupation, okay? So these are things that we just have to know that they happen, know that, how we would discuss them if somebody asked us about them, but not so important that it basically, it's not changing from our primary variables that we care about. So in this case, if this is what our model was, In this case, experience squared, married, and union. Okay? So this, just thinking about it helps in trying to understand the model, what it's actually doing. Okay? And then with the CRE, it'd be the same thing. I basically go through and take the mean, but of course I throw out these top three and only take the mean of the other ones. And then once I ran this model, the regular education and race variables would stay in, so I don't need the mean for them. And I would be able to basically make a comparison across those models. Okay? So key here is use the packages to help, but know what variables need to go in and which ones don't. Also, variables that you wish to stay in, that are time invariant, figure out a way of keeping them in by interacting them with variables that are varying over time. But once you're done, make sure that when you're discussing them as your interpretation, make sure you stick to that interpretation. It's no longer education. It's sort of a mix between whatever you interacted it with. Okay? So that doesn't really change that much. But I wanted to make sure that you just kind of gave an idea of how to run these, how to go about identifying. So somebody was asking about the XT set. See, we're defining the index here. So that's why we don't have to actually define this as a panel already. But there are packages just like in Stata that allow you to go ahead and define it, and it keeps it ordered in that set. And that is important when it comes to taking lags or, looking at taking differences within those outcomes. This package does it, but say that you wanted to do it. Then that's where you would want to use that package to define it as a panel. Once you have that, then you could do those same type procedures. Okay? Or sometimes I get lazy and don't worry about, the reason I'm telling you that there is a package is because I forget to load it sometimes. I use basically Duplar to basically do those differences for me because it can group by the individuals and then basically do it the way I want to do it. I sometimes forget to load those packages. Okay? But they're all the same thing. It's just kind of keeping track of what's varying and what's not. Okay? And then when I upload these again, like I said, I'm going to have that little note in there because I didn't before. And like I said, I don't want to see 3 months later you looking at these and you thinking that you run the dummy variable model with those time invariants. So I just put a little note saying they should be excluded. This is more of an example to show you that be careful because packages will sometimes give you information that it shouldn't. Okay, so that was just linear models in our case. Like I said, a lot of you are familiar with those. It's just, like I said, I've just seen so many times where people are running these models and basically they accept whatever it's giving. But you have to make sure that whatever the variables are including, that they're doing, the ones that should be excluded are excluded, the ones that are included should be included. Because the packages sometimes will give you back things that, usually it's very obvious. You'll see something that has a coefficient that's close to 0 and the standard error is like 100. It's very obvious that it was trying and it was becoming a singular type matrix when it was trying to actually estimate. That's why the estimates look so poor. And that's sort of a hint that they should probably be excluded in some cases. Okay, so that is linear panels. When it comes to nonlinear, sorry. Yeah.
I wanted to ask, when do we factor a variable?
When it's meant to be if you're trying to turn it into a dummy variable, that's when we would factor it.
So we don't factor occupation?
You could. I don't think the data set had a variable called occupation. They had already created the dummy variables. That's why I didn't factor them. I could have done, remember the other day I told you to combine them if I had done that code and then factored that variable, that would have been the same thing as keeping in all the binary occupation variables except one. So that's why it's usually factor is usually whenever we want to not have to create the dummy variable explicitly. It's like if we just want to keep it in the data set, but we don't want to sit there and create a new variable that is, say we had gender, and we just want to keep it as, you know, female, male, then we could say use factor. Yeah, but see, in that case, there's a little bit of a funny thing with that. So if you do that, what it chooses which one to do 0, 1. But you can tell it which one to use as your base, which would become the 0 in that case. Okay? So there's little things that you just need to make sure that if you factor it, know what it's set to 1 so that you have a good idea. That you're not guessing it was supposed to be representing male when it's actually representing female. But in this case, I didn't really care about which one it threw out of the base. Like year, I didn't really care. It could throw out any, I'm fine with it. But with gender, if that's going to be sort of your research questions about gender, you need to make sure which one is creating as a base. Okay, so for nonlinear panels, this is where we just have a little bit of an issue, because remember that we have a lot of models in here that we're using MLE or other types of methods, and there is no exact solution to these for the most part. In fact, you know, a lot of times they can be, you know, we're basically using numerical type methods to go about in the estimation procedures. So with few exceptions, nonlinear panel models attempt to deal with the unobserved heterogeneity via some version of fixed effects, dummy variable procedures. And when they do this, typically we get estimates that are biased or not consistent, because t is fixed and n is going to infinity. Basically, the number of groups that we have are fixed, and basically t is, you know, well, t is fixed and n is going to infinity. And think about it. Think about the dummy variable approach, what we did. If n is going that high, we're adding on to each parameter that we have to estimate. It's one new parameter as we go along. That's problematic. Okay? So in that case, we end up with methods that are in some ways not strictly comparable across all types of models that we consider nonlinear. So we're no longer in the linear, we don't have the linear approach to deal with. We can't try to deal with it through within transformations. We can't try to deal with it by demeaning. We can't try to, first differencing. We can't try to deal with it through adding a dummy variable for every unit within our data set. Okay, because this leads to bias or them not being consistent. So even in cases where we do find a strategy that can mitigate any type of problem, or tries to mitigate the problem of the incidental parameter, in this case AI, in that case, they're not like a one-size-fits-all. Okay? To give you an example, under certain conditions, you can go through the book, I don't want to go through all of the types of examples, we have ways of running what we consider fixed effects logit models, in the sense that we condition on the AI term. But by conditioning, we don't actually estimate it. Okay? So that means we're able to condition on it to get an unbiased estimate of the variable of interest, but what about the predictions on those? Remember, when we do predictions, we're actually using the variables of interest and all the other variables. If it's not estimated, it's assumed 0. What does that mean for our predictions? It's problematic there. Okay, so in other cases, we do find ways around this. So one GLM type model that's okay with including sort of a version of fixed effects is Poisson models. Okay. You also have negative binomial models. There's a few other ones that go in there. Or these really great econometricians have figured out ways to basically they keep running the estimations over and over again until they've figured out the effect is 0 or to a constant for the fixed effects. That means it's sort of like conditioning with the Logit. We're able to get the unbiased effect, or hopefully unbiased or consistent effect on the variables of interest. But all the things that I've just discussed, they're not, whatever I'd used in, say, the Logit can't go across all the models. Okay? What I use there's a few things I'm going to show you in quantile models. There are so many different procedures for dealing with things, but they all have little quirks to them that you have to understand that it's assuming certain things, and those assumptions kind of go, some people say that they go against the actual reason for using these methods or the estimator in the first place. So it's basically just saying there's a huge question mark here, and you have to be very, I'm going to be very general for right now. But if you really want to use those methods in trying to deal in a panel type setting, you really need to go in that literature that basically will take you down the rabbit hole for that particular type of modeling strategy. Trust me, I did this with quantiles. It was deep, and it's still expanding in many different areas, in many different ways. But it's not, it's nice because it basically can improve what you're doing, but it is more complex in trying to explain it to an audience. And explaining that it's not just like you run this and these are the assumptions I make. You have to actually say, within your context, how is that assumption holding for your context? How is the next assumption holding for your context? You have to go really deep into understanding and keeping, it's not just I'm running this because it works. You have to go a little bit deeper than that. Okay? So I'm going to give a demonstration in terms of the Logits. The reason why is because I can actually show various methods with that in terms of R. So most of these that I'm going to show can apply to the ordered side or the multinomial side in some cases. Okay? And then previously, we've argued that basically MLE is consistent when the number of parameters is fixed and the sample size increases. But with panels, we've already said the number of parameters grows with the sample size. Basically, that means each time we're adding onto our sample, we have more and more parameters to estimate, especially if we're going to try to deal with this unobserved heterogeneity. So basically, in that case, in those cases, we're not going to get a consistent estimate. And this is what I meant earlier. Remember, I told you in the linear model, it's not as problematic for us. There's some inconsistencies in our estimates of the incidental parameters. There might be, but it's not as big of a problem. In the case here, that is that smearing effect I was talking about. Basically, the inconsistent estimates and the incidental parameters leads into problems with everything else. Okay? If you wanted to put something other on this title other than nonlinear estimation of panels, it's basically a big warning sign. Basically what's going on there. And so the reason why is because a lot of times what happens is we're basically having to model these in sort of with a conditional density, and we're having to assume a functional form to what we're actually estimating. And this leads to, we can write it out in a very similar pattern that we did before, but then we're just adding in this now CI that apparently this is the slides where I started shifting from AI to CI. And in that case, we're just adding it to our original XI beta. So each nonlinear model is going to have its own specification. We're making an assumption. Remember, Probit, normal. Logit, logistic. Okay? When you're thinking about quantile models, we're agnostic about the distribution. When we're thinking about Poisson, we're assuming a Poisson distribution. But one thing I've sort of left out, and you can go in and look in this on your own, we also have models that we call pseudo Poissons or pseudo other versions that are, the assumptions are a little bit different, but we have some wiggle room there. So I'll let you look into those as well, but there is some ways of getting away from assuming specific information about the distribution. So when it comes to the conditional mean models that we have, which we still have within the nonlinear world, we can do it in an additive form. So basically everything is added into the base model. But remember, so what we're doing is if we wanted to try to include it in this function, we'd have to make an assumption about how the CI is actually entering into the model. Or we can keep it out, but still it's not contained within the specific function that we're looking at. Okay, so there's different ways of looking at this. Or it could be multiplicative, which is a whole other mess. Okay, so these are different ways that we have the unobserved effects kind of entering into our equation, our expectations. In this case, when we're thinking about it in terms of the additive, we're thinking about the CI sort of is shifting, the individual effect is sort of shifting the baseline outcome relative to some baseline of 0. Basically, we're just seeing how it's moving around. In terms of the multiplicative, is entering or is measured relative to a baseline of 1. Basically, it's thinking about it shifting around, up and down in terms of the function here. Okay, so just note the regressors, the XIT includes an intercept, just like always. So that in the additive model, the CI represents the deviation from 1, while in the multiplicative model, it's the deviation from 1. Okay, those are probably non-needed, not as important for what you're going to be doing in the applied side, but could be, well, yeah, I'll leave that alone, never mind. So in nonlinear models and panels with fixed time dimensions, like I said, the CI cannot be consistently estimated. Again, I should say in some nonlinear panels. So in terms of the incidental parameter, problems arises because the number of CI grows within, and basically it's because of the methods we're having to use. Okay, basically numerical methods. And we're having to jointly estimate the betas and the CIs in this case, and that's where the inconsistency lies. So all the traditional models, or the traditional methods we use in linear, are mostly out. Does not mean that people don't try. I should point that out too. People will throw in dummy variables into a Probit model. They will throw in dummy variables into a Logit model, Poisson, or anything else. Okay? And whether that's right or wrong is basically on their assumptions. What they're basically assuming is that the addition of these variables and their sample is large enough to where it reduces the incidental parameter problem. So if we can have t and n growing, we can try to get past or at least reduce the bias or mitigate it a little bit by having very large samples. There is some literature on that as well. But for context, usually those are big assumptions just to say that it's not going to cause incidental parameters problem. Okay? So you can do it. Whether you should be doing or not is a different story. Okay, so I leave that to you. I've seen it done in research. So that's mostly on your choices. So in some cases we can, like I said, condition on CI basically via sufficient statistics in YIT. You find that in the Logit, the Poisson, and the negative binomial. But this is why I brought this one up earlier, that the CRE is being used more and more in these models. Because remember, it's not including a dummy variable, it's not demeaning, it's trying to model the AI term, or the CI term in this case. And it's only adding the number of parameters, the means of the parameters that are changing over time. That is not the same as adding a bunch of new parameters for each individual. So you're not actually adding a bunch of new parameters. You might only be adding 5, 6, 7, versus if it's 100 individuals, 99. Okay? And because it's an approximation, and there's some error in there and everything, it's not as if you were trying to add in and specifically design the model to handle every particular person with that dummy variable. Okay, so that's where the CRE sort of works in your advantage. And there are a few bias-corrected approaches. I have seen these, and they actually perform pretty well. Okay, under most conditions, they perform pretty well. So that's the thing about it now. So sometimes we're only left with adding dummy variables. That's the only option we have. But if we know it's causing problems, we know it's causing bias, what if we can design a method that actually tries to mitigate it? And I'm going to show you that as well. Well, I'm going to let the program show it to you. I'm not going to try and attempt to do the math. But they are available to you, and you should always, if you are going to do this, try it in the sense of trying to mitigate this problem. Just don't ignore it. At least try to mitigate it if possible. Okay? And one of those is split knife bias correction. I've used that for some models. The one that's going to be, I'm going to show you in a minute with a program, is going to be more of an analytical approach to reducing it as well. And that's only two of a lot of different methods to do it. There's this whole literature on just trying to mitigate this problem in nonlinear panels. So note that even if beta is consistently estimated, the overall mean effect may not be. So especially in multiplicative models, just keep that in mind. Even though we're trying here, we can still have some issues with our estimates of the CI. So the practical approach basically is, I'm bringing this in again. Basically, in terms of the binary at least, maybe it might be better to go back to an LPM model. Linear, doesn't mind fixed effects, runs fast. You only care about the average, might do a decent job. Okay? So always keep that in the back of your head. Just because you're trying to advance either your research or anything, sometimes just jumping to the most complicated model isn't always the easy or the best thing to do first. Check the simpler, then add the complications. Okay? So this strategy typically can yield reasonable estimates of the average without the need of strong conditional independence assumptions as well in this case, as we've already seen that it works well. We can look at just basically adding dummy variables for each individual for the OLS outcomes, and it doesn't do a bad job. Okay. So further notes, basically with the fixed effects method in some models, I'm just kind of going back to this conditional type maximum-like estimation, basically using the sufficient statistic. In case of the Poisson, and there's always going to be related to the Logit, this should be consistent in those estimations. But I just wanted to point out there's a growing literature here that basically shows how to run something we call high-dimensional fixed effects. Remember before when I told you I was running trade models and I had close to 33,000 paired outcomes that I needed to control for? There are methods that actually deal, or I shouldn't say deal, they actually control for all those dummy variables I would typically have to add, and the algorithms they use are very quick. So if you are in that OLS type world and you have a lot of different fixed effects to add, it's advisable to sort of use these methods because basically, one, it's going to be a lot quicker, and I mean a lot quicker. Two, they also make adjustments for the standard errors, allowing for clustering, two-way clustering, and it's just a simplification on your life for those. The ones that I know about mostly are the OLS versions of this and the Poisson versions of this, but I would not be surprised if there are other versions. Okay? And then basically I said the random effects models, we assume that CI, distribution for CI is in there with the parameters. Hold on, what is that? Oh, within these models, typically, if you're using state or anything, you'll see something in those models and they'll say XT Poisson, XT Logit. I'm trying to remember all the ones I have. XT ordered Logit, XT M Logit, all those that they have. You'll see a lot of times whenever you're actually looking at the command, you go into it, you'll actually see that it's only for random effects. Okay? It's not made for fixed effects. So make sure you do that. Just because you find something, especially if you're using, I know this from Stata, there are some in R as well. Make sure that it actually works for fixed effects and it's not just for panels and assumptions in terms of random effects. Okay? Make sure it's really going to be used for what you want. And then, like I said, I guess I keep pushing that one in terms of the correlated random effects. I've had a lot of success with that. Doesn't mean there's any fewer assumptions, though. I should point that out. There's just as many assumptions under that case as with a lot of other methods. Okay? So when it comes to the Probit and Logit, recall the specification in terms of we're looking at the probability of success given the right-hand side variables, and now we've added the CI. We're basically entering in the CI into our particular G function here. And we could add in time dummies, interactions, and other things included in there. And if we were to try to run the partial effects or marginal effects, basically just kind of get in your head that basically what we're doing is we're having to actually adjust here. Right? Because it's still within that function. We have to take the linear outcome within that function. Then we push it through the link function. Because the CI is unobserved, we must address its influence within inside. So there's going to need to be some assumptions about the distribution. And assumptions under the estimation, we usually are trying to do it under strict exogeneity. So conditional independence is assumed assumed in that YIT for all T in this case, given the R independent given XIT and CI. Similar to the assumptions we had before. Basically, we need this to, in some ways, if you want to call what you're looking at as causal, you would require this. Okay? Under the conditional logit, I've kind of mentioned this before, basically, conditional logit is widely used in research. Okay? We can condition on the individual units. Basically, the program will take care of that for us. We'll get an unbiased estimate on the variables of interest, and basically we've accounted for that individual specific outcome. So the model, that's basically what is going on here. Basically we're saying it's providing a consistent estimate by conditioning. But you note that I'm not saying that I'm actually estimating CI or removing CI. I'm having a condition on it. So all the applications we usually focus on that I know are basically in labor and health economics. But the important note of this is basically the model conditions on CI but does not estimate it. So remember, we need a prediction to feed into the, in our case, this would be the logistic function. And that's the link going back to linking it to probabilities. If I have 100 individuals, so that means I should have had CIs, 99 of them, if it's dummy variables. That should be into the prediction. Now, they're not estimated. They're just conditioned upon. What happens with my propensity score? It's basically, in some ways, your programs are basically assuming that all the individual effects are zeros. But you said they were important. So which is it? So you just have to be careful with that. That basically, you can do that and get estimates on the conditional Logit for the variables of interest, but basically the implication is that the propensity scores and the marginal effects cannot be properly calculated by the usual steps that you do within your that you're familiar with. There are ways of doing this, but I'll tell you the methods are very complicated. Okay. So some softwares will, I run something in, say, Stata, C Logit. Then I ask it for the marginal effects. Margins, comma, dy, dx, variable I'm interested in. It'll give you an answer. But if you look at the actual information in the help files and everything else, it'll say that when it made that prediction, it assumed that the fixed effects were 0. Or I think you can also assume the fixed effects are 1. But other than that, there's not too many choices there. All right? So if your primary concern, you want to be able to talk about the marginal effects, the effects on the probability, you're kind of left with trying to figure out what to do. Okay, so just keep that in mind when you're doing this. So basically you will get something that comes out, but it's going to make certain assumptions about the CI term since it wasn't explicitly estimated. That's why I'm always saying not only know your data, your method, but also know the program if you're going to use it, what exactly it's assuming. Because it can be a surprise about what actually is coming out once you know what it's making assumptions about. Okay? Okay, so that's actually lunch now. So we'll continue on after lunch with the correlated random effects.